This is part 5 of section 5.1, trigonometric substitutions. Sometimes in calculus, you will find it necessary to convert an algebraic expression into a trig one. And this technique is called trigonometric substitution. Now, by the time you get into calculus, they're going to want you to know what substitutions to make, but you're far from being ready for that at this point. We're just going to work some problems that will kind of show how it works, okay? So we have these problems that say make the indicated trig substitution in the algebraic expression and simplify. And we're told to assume that our angle is between 0 and pi over 2, which is really nice because all of our trig functions are positive in that quadrant, so we don't have to worry about signs or anything else. We just get to do our most basic work, okay? So if we're given the square root of 4 minus x squared, and they want us to make the substitution where x is equal to cosine of 2 times cosine theta. Well, if I simply make that substitution, I have square root of 4 minus, if I square this, I have 4 cosine squared of theta. Okay. Now I can factor a 4 out of that. Okay. 1 minus cosine squared theta is equal to sine squared theta. And now we have two things multiplied together under a square root, so we can take the square root of both sides. And again, we know everything here is positive because of what quadrant we're in, so we don't have to worry about a plus or minus or anything when we do this. This is just going to be 2 sine theta. Okay, similar problem here. We're given x over the square root of x squared minus 16, and they want us to substitute 4 cosecant theta for x. So this would be 4 cosecant theta over the square root of, if I square this, I get 16 cosecant squared of theta minus 16. Factor a 16 out of this to get cosecant squared theta minus 1. Cosecant squared theta minus 1 is cotangent. So I have 4 cosecant theta is equal to the square root of 16 cotangent squared theta. So this is 4 cosecant theta over 4 cotangent theta. The 4's cancel. And as these involve sines and cosines, chances are it simplifies some as well. If I do cosecant theta, writing it as a sine, that's 1 over sine of theta, and I want to divide that by cotangent, which is cosine theta over sine theta. Multiplying by the reciprocal, I end up with 1 over cosine, which is secant of theta. Okay, and I decided to work one problem from the beyond the basics section. Okay, they want us to verify this identity. And what I'm going to do is I'm going to do binomial squares here. I'm going to multiply these out and hope I end up over here somewhere. Okay, so my left-hand side is equal to, when you square a binomial, you square your first term, which is 1. You write the sign from the middle. You multiply them together and then double it, so that's going to be 2 tangent x plus, that's always a plus, square the last one, tangent squared x. Okay, plus, I'm going to do the same thing here. You get 1 minus, multiply together, and then double, so that's 2 cotangent x plus cotangent squared of x. Okay, and I'm hoping to end up with secants and cosecants, so just sines and cosines. Okay, so let's see what we've got here. I have these two with squares and I have ones with them as well. So I can easily rewrite this as 1 plus tangent squared of x. Put that in parentheses, and I've dealt with this one and this one. Plus 1 plus cotangent squared of x, using this one and this one. And then I have these two, and I can factor a 2 out of that, right? So I have tangent x plus cotangent x. Now, why did I do these? Because these are Pythagorean identities. 1 plus tangent squared of x is secant squared x. Plus 1 plus cotangent squared x is cosecant squared x. Okay, and minus 2 times, let's go ahead and write these as sines and cosines. So I'll have sine x over cosine x plus cosine x over sine x. So getting a common denominator in here and combining, I'll have secant squared x plus cosecant squared x minus 2 times, it's going to be sine squared x plus cosine squared x over cosine x sine x. This is a Pythagorean identity. It is 1, so I have secant squared x plus cosecant squared x minus 2 times 1 over cosine x sine x. And these I can write in terms of secant and cosecant. And I'm going to rearrange this just a little bit. I'll have secant squared of x minus 2 times secant x cosecant x plus cosecant squared x. Now, why did I do all this? Because if I were to multiply this out, I would get exactly this. Squaring a binomial, you'd square your first term, secant squared x. Write the sign from the middle, multiply them together and double it, plus your last one squared. This is a perfect square trinomial. It factors as secant x minus cosecant x squared, which is the right-hand side, and the identity is proven.